In this lecture, we're going to look at pericyclic reactions. This is chapter 4 from Grossman. And this is one of the topics that always breaks my heart to kind of blitz through in this format. It's a really enjoyable set of reactions, kind of really thought-provoking in terms of the types of things, the types of transformations that can happen in the universe, that sort of thing. Because we move away from things with actual charges. We've seen some of this stuff before in organic too, but a lot of this is my guess. My guesses will be a review to many, and that is great. Okay, so anyway, pericyclic reactions. This is a class of reactions in which bonds are formed and broken at the ends of pi, one or more conjugated pi systems. Okay, so a lot of words there. I at least wanted to say it. So a class of reactions in which bonds are formed and broken. We can actually go in either direction at the ends of one or more conjugated pi systems. Okay, I'll put the conjugated in parentheses. It's often conjugated, but I'm sure I can think of probably a few exceptions of that if we need to. But okay, so let's immediately go into the types of pericyclic reactions. And so we have, at first, we have electrocyclizations. And these can be either ring closures or ring opening reactions. But if we define them in the context of ring closing reactions, they could be ring closing reactions in which sigma bonds form a new ring from the end of pi bonds. Now, okay, mentally, I can't think of like an exception to this rule, but there has to be like several exceptions. But I'm going to, instead of writing always, I'm going to write often. These are unimolecular reactions. And maybe another word is /intramolecular. That is, these types of reactions occur within the molecule. So within the self of the molecule or whatever, these types of reactions occur. Okay, so there's a key driving force for these reactions before we get into several examples. The driving force is the formation of strong sigma bonds at the expense of weaker pi bonds. Okay. That's always an important feature of these reactions, is to think about why they go in a particular direction. And it's because the head-to-head overlap of sigma bonds is a lot more energetically favorable than the side-to-side overlap required for pi bonding. And so my favorite example is the 6-pi electrocyclic ring closure. Closure, okay, or ring closing reaction. So this looks a lot like, or is reminiscent of, a Diels-Alder reaction, but we'll look at those types of reactions here in a second. Diels-Alder reactions are different because they're not always, definitely not always, but in many cases they're bimolecular reactions. And just so you're aware of the terminology that's coming, we would call those cycloaddition reactions, which is a different word than electrocyclic reaction, and for good reason. These things are just different transformations overall and have different steric requirements. And so if we look at this, we start with 3 pi bonds. That is 3 second bonds between 2 carbon atoms, 3 pi bonds. And at the end of the reaction, we have 2 pi bonds, and then 1 sigma bond is new. So there were already several sigma bonds, but the sigma bond changes 1, and the pi bond changes -1. And so you lose a pi bond, you pick up a sigma bond. This makes this an energetically favorable process. And this is what allows for the reaction to actually occur, because it turns out that this is reversible. Okay, now I didn't actually mention the conditions, I just wrote the name. So the conditions are heat or light for this reaction. So we write heat for the like alchemist symbol for fire, I learned, or also just delta energy. And then HV for Planck's constant times the frequency of a photon gives you some energy of a photon. So that's how we supply our energy. Now 3 pi bonds, which I labeled in the outset, means we have 3 times 2 equals 6 pi electrons, because we like to think of there being 2 pi electrons per second bond between 2 atoms. Okay, so this is an electrocyclic ring closure because we form a ring. So a new ring has formed. There could also be electrocyclic ring openings. Now it turns out if you take a cyclobutene, okay, and you expose this to either heat or light, you will get write the name down here, a 4 pi electrocyclic ring opening. Now what that looks like is we're actually going to move in the opposite direction that we did previously. So previously we kind of rolled the conjugated double bonds around to make a new sigma bond and then move the double bonds. Here we're going to break the sigma bond that's across from the double bonds, and we get, and by break it, I mean we're going to shove it down to make a new carbon-carbon double bond, and then shove this double bond up to make a new carbon-carbon double bond up this way. This gives us this structure, which is now a conjugated pi system, but we've lost the ring. I'm going to just let this relax, let the geometry sort of flatten out, and we get a dying. Remember the old saying, like, help me, I'm dying, right? So anyway, everybody loves that joke. Okay, so what we've done here is we've taken a monoalkene and rolled the double bond around and then broke a sigma bond to give rise to 2 new pi bonds. Pi bonds, whereas before we lost 1 sigma bond. And actually, it's not 2 new, it's 1 new pi bond, excuse me. So here we exchange a sigma bond for a pi bond. Now, why would we want to do this? The driving force doesn't seem to add up because pi bonds are weaker than sigma bonds. Well, if we look at the starting molecule, we would say the starting molecule possessed ring strain. So we had some strain and some instability built into the molecule, which was released. After the ring opening reaction. Okay, so those are electrocyclic ring closures where we form a ring, and then electrocyclic ring opening. That second example was when we actually opened up the ring. Now it's important to note that these processes can actually occur in reverse of each other. So if you really wanted to, excuse me, if you really wanted to, and let's make note of that. So ring opening and ring closing reactions and I should have qualified this as saying electrocyclic ring opening and ring closing reactions are the reverse of each other. Okay, kind of an interesting equilibrium that we can observe is if we actually start, I just gave away the punchline of the joke, but let's start with this non-aromatic molecule. It might actually be aromatic if I consider a resonance structure. I should know that before I start recording the lecture, but I think I'm already 5 minutes in, so I'll have to look that up after the fact. Because we could consider a resonance structure like this. It's kind of a permanent dipole to induce aromaticity. I'm gonna cross this out. Anyway, if we apply heat to this, I actually don't know where the equilibrium constant lies, heat or light. We can actually flip back and forth between this and the cyclobutene structure. And then perhaps you want to see the curly arrows drawn this way, or you can have the curly arrows drawn this way. If we have resonance structures, we can get to any product from any resonance depiction of a molecule. Okay. So the point here is we could do ring closing and ring opening reactions are just the reverse of each other. If you can go one way, you conceivably can go the other way. Now this one's a really interesting equilibrium because it's got a driving force towards less ring strain, but a permanent dipole to get to aromaticity, or no aromaticity, which isn't a good situation. Or you could absorb that ring strain, deal with it, and get to a permanently aromatic molecule. Although we have some kind of twisted bonds in there. Yeah, it's a really interesting molecule. Okay, what I want to do is take a second and just go back to the 6-pi electrocyclization. So we could consider the reverse of that if we wanted to. So the reverse of the 6-pi electrocyclization would be where we start with the ring closed product and then we move the bonds around. Now that's not a super favorable process because we're not alleviating ring strain to do the electrocyclic ring opening, and we're building in a new pi bond. But you can draw the arrows there if you need to. So maybe there's something else to offset that energetic cost and perhaps drive the reaction towards the product, which would be kind of interesting. So ring opening, ring closing reactions work together. Now these things can get kind of funky in some ways. I'm going to leave that description there. And I'll go on the record as calling some chemistry funky. So what I want to do is consider this cyclopropanone substrate. So it's just a cyclopropane with a carbonyl. And cyclopropanes are weird, but they're not uncommon. And if you apply heat or light to this, you can actually access what's called a dipolar intermediate, where you've got this enolate structure next to a carbocation. Now, how did that form? Well, there's a few ways that you could think about forming this product. Looks like I need to build some paper here. Sorry. Let's see if I can add the pages without freaking out. There we go. Okay. Sorry about that. Okay, what we could do is we could consider a resonance structure of this where we've got the carbonyl separated as a negative on oxygen, a positive on carbon. And then all we have to do is just shove one of the bonds over to make a carbon-carbon double bond and leave behind a positive charge, which would be at this position. And I'm not sure if you can trap that dipole, you can actually push this intermediate or this equilibrium towards the product. So that's one way to draw it. And alternatively, what you could do is you could go from here to give rise to the product. Remember, any resonance depiction can get to the product. Resonance depictions are depictions of the same molecule. If you do a good job drawing resonance structures, you can actually get to any product. Any resonance structure can get to any product. That's my point. Okay. If you have questions about that, let me know. Okay, so these things can get kind of interesting. I don't know, maybe we call this a 2-pi electrocyclic ring opening. It's kind of interesting. But anyway, so those are electrocyclization reactions, and they come in a lot of different flavors with a lot of different electron counts. And from organic chemistry 2, this is where you use the thumb trick to think about conrotatory and disrotatory ring opening to predict stereochemistry of the product. And there's a nice section in the textbook on that. Next, we're going to go into cycloaddition reactions. And by far, my favorite cycloaddition reaction is the Diels-Alder reaction. But it's not the only cycloaddition. Let's get that out there. The Diels-Alder cycloaddition. So in the Diels-Alder cycloaddition reaction, what we do is we first of all call this a 4+2, and those go in brackets for some reason, cycloaddition reaction. So in the 4+2 cycloaddition reaction, we take a diene and we add it to an alkene, an alkene that we label as the dienophile, telling us that that is the alkene, that is the molecule that possesses the pi bond that's going to react with the Diels-Alder diene to give the cycloaddition product. So here these two things add together. We draw these 4+2 arrows to give rise to a 6-membered ring with one double bond, and then all the groups sort of hanging off of it. Okay, now what's important to note is that I could have the orientation of the diene or the dienophile sort of flipped in this case because I don't have a symmetric diene and dienophile. That is to say, I could go here. I'm going to leave the diene alone, but I'm going to rotate the dienophile such that now we have the carbonyl now closer to the methyl group. Now, what's important to note is that these two structures are isomers of each other, and I would classify them as what's called a Regio isomer, because these two structures have sort of reacted at different sites or regions of the molecule. Okay, the Regio isomer word works really well if you have multiple types of the same type of functional group present, but it's harder to understand here. But what we say here is that we're reacting with different, I guess, orientations of the p orbitals that have to overlap. If you remember all of those perspective drawings. Anyway, I could belabor that point probably too much and hit diminishing returns quickly. So let's go ahead and look at some examples that are sort of fun. So I think this is a fun example. We're going to pick on the same diene structure that we had earlier, or excuse me, the same polyene structure that we had earlier. And I'm going to focus on this part to be the diene. Now it actually sort of looks like there's two dienes present, but this one is the more reactive pair of pi bonds, because if it finds a monoene, I'm going to label this diene in yellow, and I'm going to label this dienophile in a different color. So we're going to react with this pi bond, And if we do the 4+2 cycloaddition here, we actually generate an aromatic benzene ring in our product. Oops, I don't want to rotate those. I want to be careful about my double bonds so you guys can see this. It does not matter though. So we actually form 3 rings in the product. If you want, I can trace the various bonds. So here were the carbon atoms involved in the dienophile structure, and then in yellow, here are the carbon atoms involved in the diene structure. So it's pretty cool because you generate an aromatic ring during the course of the Diels-Alder reaction. Now, let's look at an example where we actually, instead of picking a typical diene, dienophile, we could pick a diene. Okay, so, or excuse me, an alkyne to be the dienophile. Let me say that again. I'm replacing the dienophile, which is just a monoene in many cases, with an alkyne. I've added another site of unsaturation. I've added another double bond present. Okay, so here's my diene. Hopefully you can see that clearly. And then here is my dienophile. One of those pi bonds on the triple bond. The other one is unreactive under these conditions and won't engage with the diene. And what that results in is a 6-membered ring with 1 double bond here, which is part of the diene, and we should attach the methyl groups. And then we have CH3s here and here. Maybe I should have picked different groups. They're going to be right here and right here. Now, typically, if we used a typical dienophile, we would be done. But because we used an alkyne, we still have a pi bond left over between the 2 carbons of the dienophile. Let's make that green, which means we have another double bond right here. So we have 2 double bonds in the products because we've included an alkyne. This is what we call a dihydro-Diels-Alder reaction. And that's because one reactant, we say, has lost 2 H atoms. And in fact, something I studied in grad school that was actually a lot of fun was the Hexadehydrogel reaction. Now, this isn't, it turns out, mechanistically a true cycloaddition reaction. So I'm going to push arrows that allow you to see what's going on here, but there is a lot of radical character in this mechanism, probably not surprising given how awkward the structures are. Whoops, hexadehydrogel reaction. Hexadehydro, excuse me. So in this reaction, we're going to, instead of removing 2 hydrogens to give us the didehydro, we're going to remove 6. That is, we're going to take our diene and remove 4 hydrogens from it. So I'm going to cross all of these out and replace them with additional double bonds. That's going to give us a diene, a dialkyne, and we're going to add that to an alkyne, which again is like taking our alkene and removing 2 hydrogens from it to give the dialkyne. Now, when you do this reaction, let's push the arrows again. Imagine these are actually radicals, but allows us to see how things get pushed around. Now, when you do this, stuff gets weird. First of all, you've got a crazy structure that you have to sort of try to relax. So here's our structure. We've got a bunch of double bonds present, but let's go ahead and try our best to relax this into a 6-membered ring. So just like before, we're going to have a double bond all the way over to the right. And then now we're going to have double bonds here and then double bonds here. Now this is highly questionable at these 2 positions because they look as though they have only got two substituents attached to them and perhaps have a lot of sp hybridization character as opposed to sp2 hybridization, which is awkward. Okay, I agree. So what I want to do is I'm going to draw a resonance structure where I roll all of the electrons around. If you think about it, it looks just like how we roll the electrons around in benzene. One of these arrows is a little sloppy. And that double bond looks a little sloppy. So I'm just going to clean that up so you can see. All right, so I'm going to go from bond to bond in every case. Now, when I do that, again, I'm considering a resonance depiction where we now have two pi bonds at the leftmost carbon and then a typical kind of benzene-like arrangement. Now, this overall molecule is near and dear to my heart. This is benzene with an alkyne in it. This is instead benzyne. Benzyne is a really interesting reactive intermediate. You can't, as far as I'm concerned, really put it into a bottle in any appreciable way, practical way, I'll say. But it's highly electrophilic, and so it will engage almost any nucleophile that's on the shelf. Sometimes solvents are not even that compatible with it that we would typically use. Additionally, it's a good reactant in a lot of cycloaddition reactions. And so you can even do Diels-Alder reactions on top of this, which is called domino sort of hexadehydro Diels-Alder reaction. So really fun chemistry, and I can talk about it in more detail if anyone is interested. Okay, but all of these, well, the hexadehydro Diels-Alder reaction is a bit of an exception to say the least, but most of these are all sort of 4+2 cycloadditions that we were looking at. Are there any other types of cycloadditions? And indeed, you could have 2+2 cycloaddition reactions. So in 2+2 cycloaddition reactions, what you do is you take an alkene plus an alkene, two pi bonded systems, and just let them engage with each other. I'm going to draw arrows kind of going out into nowhere, but it's sort of to show the connection point between the two ends of the pi systems. Okay, just like sort of how we did the Diels-Alder reaction, but it was a little bit, well, not in the hexadehydro case. If we look up at the top of the screen here, we had those arrows kind of connecting the termini of the diene to the carbon, the pi bonded carbons of the dienophile. So we're going to do something similar here, and we're going to get a highly strained four-membered ring. So we have our new bonds as part of, in this case, four-membered rings. Four-membered rings. And so what these do is these generate a lot of ring strain. Which means that they require energy input. There's usually a high reaction barrier or activation energy, as I could more precisely say. So you have to do some special stuff to get this to actually work. So if you want to use regular alkenes, just like a typical carbon-carbon double bond, you need to apply photochemical conditions. It's kind of a weird word, photochemical conditions. Let's just say photons are the energy source. Then it's not a weird word at all, because we've talked about using H-nu a lot in class. So what I'm saying is if we have some sort of alkene with some R groups, and let's go ahead and make it Z. And we've got R2s over here for another alkene that's also Z. What I'm saying here is you could apply H-nu to this reaction and form the 2+2 product. Now, just like the Diels-Alder reaction, it's a little, or the hexadehydro Diels-Alder reaction, it's a little bit disingenuous to draw the arrows connecting with each other like I've done at the top of the page here. And that's because this reaction has a lot of radical character with it. Now, in many cases, what happens is that one of the alkenes gets excited by the H nu, and the pi bond electrons separate into a biradical system, which can engage with the second alkene. Typically, if these things are different, one absorbs a little bit better or can kind of take on the energy of the photon a little bit easier. So then we have a radical adding to a pi bond where it splits the pi bond in half, pushing one electron over to make a new bond, which is down below. And then the other pi electron that was once part of the double bond is now on the carbon that didn't form a new bond, but that's now in close proximity to the first carbon that had a radical from the photon-induced conditions, and those two can just buddy up to make a new bond. We have new bonds in the top and the bottom to generate the ring system. So that's one approach to doing the 2+2 cycloaddition. Alternatively, you can use some sp hybridized containing carbon containing alkenes. Okay. So let's go ahead and move right into, well, we'll capture that thought, but then we'll move right into some pictures. So alternatively, use alkenes with sp hybrid carbon atoms. And so what that looks like is, let's say we take our just a run-of-the-mill alkene, put it inside a 5-membered ring. We're going to add that to another alkene, this time under thermal conditions, but we're going to make that other alkene have an sp hybridized carbon atom. So typically you would use a ketene. So ketenes, we've looked at in organic 2. These were intermediates from the dehydrohalogenation of acid halides, which was towards the end of this semester. So they're pretty easy to make. You just take some sort of acid chloride, carbonyl with a chlorine attached to it, treat under basic conditions to eliminate HCl and form a carbon-carbon double bond on a carbon that also has a carbon-oxygen double bond. Okay, so this is a ketene, carbonyl alkene, I guess. A ketone alkene. I think that's where the name comes from. Or you can add it to an allene, which we talked about in the stereochemistry section of the course, where we have an sp hybridized carbon atom between 2 carbon-carbon double bonds. And I guess I'll just redraw the 2+2 addict. Now what you're going to do is pick a carbon-carbon double bond to react. And here you would get this 5-4 system. Well, I guess in both cases you'll get a 5-4 system. It's just one has a carbonyl, the other one has a carbon-carbon double bond. Okay, so some funky reactions, but they find a way to make the orbitals overlap without violating any important symmetry rules called the Woodward-Hoffman rules, which we can talk about in more detail. I think it is outlined in the textbook. To do this, though, you really unless you're going to expose these things to light, and these things can happen under heat just fine for the most part. They're not the most efficient reactions, but if you can put a ketene in a bottle, you can do this sort of reaction. And you get some interesting stereoselectivities that are highlighted in the book too. But otherwise, this is the trick to getting 2+2 cycloadditions to work using sp hybridized carbon atom. Lacks a lot of steric hindrance, has more accessible orbitals, and that sort of thing. Anyway, hopefully you enjoyed the lecture.